Okay, welcome back. So in this video, we're going to do example 2. This should be rather quick. I just want to knock out some examples. So we were given this integral, which is the integral of y dx minus x dy. And again, if we apply the definition exactly, this might take some time. So we don't want to do that. So instead, we want to use Green's theorem. Now, before I can apply Green's theorem, I want to make sure it's in the right form. I need the integral of p dx plus q dy. So I have my dx and then my dy, but I don't have a plus sign. So I'm just going to move that minus sign in there and write the plus sign so that it's just exactly as the book says the Green's theorem has to work. So now going from here to here, this is Green's theorem. Okay, so this is p and this is q, and it says that the derivative of q with respect to x minus the derivative of p with respect to y. This is Green's theorem. So here's my q and there's my p, and this is obviously the derivative of x with respect to x is 1, so I get minus 1 and 1, so I get minus 2, and I started off with a circle centered at the origin with radius 4, so that's what this is. So Green's theorem says I go from the outside, the boundary, and now I'm going to evaluate the inside. Now, sometimes it's going to be helpful to actually go the other way around, where you'll have the inside, and it's actually going to turn out to be easier to evaluate the boundary, the outside, for whatever reason. Maybe it's a conservative vector field, and you know those are equal to 0, so you could move it to the boundary and then use the fact that the thing on the boundary is equal to a conservative vector field and you get equal to 0. Well, in any case, this is minus 2, and I'm going to rewrite this. Well, it's a circle, right? So why not use polar coordinates? So move that minus 2 outside and then rewrite this as the integral from 0 to 2 pi, 0 to 4, which is the radius, r dr d theta, and that is the full integral. See you in the next video. Don't forget, like and subscribe.